Okay, we are recording. Well, it's a great pleasure to welcome Katrin Wendland to speak to us today. She's coming to us virtually from Freiburg, and she needs no introduction really to this audience, so I will hand over directly to you, Katrin. Thanks.
Thank you very much, Denjo, for the nice introduction and for the invitation to speak at this seminar. It's a pleasure to be here virtually, although of course I would prefer to be there in person, but this is the best we can get at the moment. And I would like to apologize for any technical mishaps with Zoom because I'm not a Zoom expert so far, and I really hope I don't have to become one. Now, the topic of today's seminar is the complex elliptic genus or complex elliptic genera. So this is part of a longer scoped research project I've been working on where I'm looking at invariants that are shared between conformal field theory and geometry. Such invariants can be useful just to think about translating stories from geometry into conformal field theory and maybe simplifying some calculations or even finding new structure. And probably the simplest such invariant that is shared by geometry and conformal field theory is the Euler characteristic, which has its counterpart in conformal field theory, where it is called the Witten genus. So in geometry, the Euler characteristic in some sense gives information about the cohomology of the manifold you're looking at, the dimension of cohomology spaces there. And on the conformal field theory side, what you're really doing is counting certain states, counting BPS states. Elliptic genera can be viewed as, well, variants of the, or refinements of the Euler characteristic. So the idea goes into a similar direction. One can actually introduce complex elliptic genera and elliptic genera in general by starting from the Euler characteristic and then refining. So by what I said earlier, this is an invariant which allows you to give some information about cohomology of the spaces that you're looking at on the one hand, and in physics about certain BPS states and the dimension of spaces of BPS states. So that's the general context here. And in particular, we've put the elliptic genus into very much use in the context of looking at conformal field theories associated to K3 surfaces. There, the complex elliptic genus is really a very valuable tool, and I would claim that I understand the elliptic genus for K3 quite well up to now. But then, as a matter of fact, K3 surfaces can obtain singularities. They're still quite mild in the K3 case, so we have them well under control, but they can occur. So it's a natural question to ask whether we can decompose the contributions to the complex elliptic genus into contributions from the singular parts and the non-singular parts separately. And that's essentially a question asked to my PhD student, Yuhang Hou. When he started with his PhD project, I wanted to know whether one can make sense of the complex elliptic genus for such surface singularities of the type that can occur in K3 surfaces, and whether one can then understand the K3 elliptic genus in terms of, well, non-singular and singular data, so to say. And this is not such an easy problem because the complex elliptic genus is tailor-made to study compact manifolds, whereas these singularities are modeled on non-compact spaces. So one has to work hard in order to come up with a useful definition of how to even define complex elliptic genera in this setting. And there are two standard methods to do this: regularization on the one hand, and making things equivariant on the other hand. And with a background in mathematical physics, when we have a choice, then we try all the choices at once, and this is actually what Yuhang did. And then we actually did find that both approaches make sense and everything fits together well at the end of the day. So Yuhang has now completed his thesis. We're working on a preprint, which should be completed hopefully soon, where we are summarizing our joint results. And this is the background of what I want to talk about today. I'll begin with a lightning review of what these elliptic genera are and how to define them and what they actually count. And then we will turn to these singularities that are of relevance here. They occur in the context of orbifolds, and the name of those special singularities is ADE type quotient singularities, or simple surface singularities. That's actually the same thing here. And then we're ready to discuss the elliptic genera for the ADE type singularities. I will present closed formulas for what we could do here, and we'll try and explain how everything fits together. And then at the end, I'll give a short explanation to an observation that we made here, namely that the ADE type singularities obey certain relations, which on first sight are unexpected, but on second sight, of course, also allow a geometric interpretation. All right, so what is the elliptic genus? I'm sorry. Now, that is one of these technical mishaps that I was predicting. Here we are. So what is the complex elliptic genus? We'll start in geometry, and as I said, we'll start with compact spaces, where the definition is fairly straightforward from a mathematical point of view. And as I already mentioned, one can start from the Euler characteristic. So if you know about the Hodge numbers of your manifold, then this is an equation you can use to calculate the Euler characteristic. And you can simplify things by packaging the sum over J here into just one expression, because that turns out to be what we call the holomorphic Euler characteristic of this bundle here, where T is the holomorphic tangent bundle. And introducing useful shorthand notation, we can even write it like this, where instead of these separate bundles, I'm pretending that I can sum them up and decorate them with prefactors, where these are just signs here. And in general, one can construct such so-called virtual bundles by just writing out formal series where the coefficients can either be a formal variable or just a number, like here, an integer in general. And that then is abbreviated by this notation here. We should say T star here is actually a dual of the holomorphic tangent bundle. And this notation here then feeds into that shorthand notation where we start with any bundle on M, and we allow ourselves to discuss all the exterior powers of E in one go by just summing them up and separating them by attaching a formal variable here. And later on, we will also need the symmetric powers like so. So this is just notation at the moment, and I'm introducing a calculus where I'm allowing chi just to be pulled through, pulled past the sum sign and past anything that I wrote here for decoration, either an integer or such a formal variable. Now, it turns out that these numbers here are already interesting invariants of the manifold that we started from. So in some sense, it's a lot of information if we just sum them up like this with signs. This is just an integer on the left-hand side, but maybe I would like to know all these separate integers. And that's how this notion of refinement can be understood. We can keep track of all these separate integers by changing our definition, by changing the -1 here into a minus y, which now is a formal variable. I've introduced it here. So -1 to the k everywhere has been replaced by a -1, but by a -y to the k. So this way, I view this as a polynomial in y, and all the coefficients are interesting because all the coefficients are then essentially these holomorphic Euler characteristics that I might be interested in. And this refinement is almost classical already. It's known as the Hülse-Bochkai-Y genus. If you want to calculate these quantities, it's important that these Euler characteristics are actually indices of certain differential operators, of Dirac operators, and they allow to be calculated through an index theorem. So using a Hülse-Bochkai-Mann-Roch index theorem, you can actually calculate these invariants by taking an integral over the full manifold and then integrating over local expressions. So if you've never seen this before, never mind. But these are expressions that we can calculate from the local data on the manifold, known in terms of so-called characteristic classes. So that's the Hülse-Bochkai-Y genus. In order to arrive at the complex elliptic genus, we need to refine this even further and quite dramatically by replacing this bundle by a virtual bundle that arises from this one by tensorizing by something that looks fairly complicated, namely by all this stuff. So that's a new virtual bundle, which goes back to what we started from. If you insert q equal to 0 here, then all these guys here become just trivial line bundles and essentially go away under the product here. And then we're back to that virtual bundle here up to a prefactor, which at the moment is just a decoration. But well, this further refinement is actually very important we're introducing yet another formal variable q, and then some complicated expression. I will say a few words about how to motivate this expression in a minute, but for the purposes of this talk, you can just view this as a black box. At the end of the day, you have an infinite power series in Y and Y inverse and in Q, and all the coefficients are just complicated vector bundles whose Euler characteristics are of interest from a geometric point of view. And then the holomorphic Euler characteristic of this guy viewed in the way that I explained up here. So I'm allowed to pull chi past the summation sign and past all the prefactors as to read off the coefficients, which are just holomorphic Euler characteristics of some bundles. This is the complex elliptic genus. And here again, I'm reminding you of this Riemann-Roch type expression, because we will actually use that later in calculation. So that's why I'm saying it here. And now it turns out that this formal power series in Q and Y inverse actually is a holomorphic function as long as you restrict to the appropriate domains for these variables. Q must live in a punctured unit disk, and Y must live in the punctured complex plane, and that's it. So it's convenient and also fashionable to write Q equal to 2 pi I tau and Y equal to 2 pi I z, where tau and z are complex numbers, and tau is taken from the upper half plane as to ensure that all this is well defined. And then you have the complex elliptic genus as a holomorphic function in tau and z with lots of beautiful properties. So this was just a quick way of introducing things from a mathematical point of view, just to be safe, to say, yeah, tick, I've explained everything, I've given you all the details, but of course, that definition is not very approachable. I'm just giving you a formula and saying that it gives you important information. But it gets filled with content if you know why people wrote it out. It's actually the result of a concerted effort between mathematics and physics, going back to Hirzebruch and Witten and others, who thought about defining a Dirac operator and its index on the loop space of the manifold M. And that's, of course, a natural space to look at when you're interested in string theory. It's infinite dimensional, so it's problematic even to talk about the Dirac operator, let alone its index. But if you keep your act together and just pull it through and introduce a U1 equivariant version, there's a fairly natural regularization that one can perform, and then one arrives precisely at the formula that I gave you on the previous transparency. But that's really where it all came from, and it's important information just to make sense of why such a quantity might be interesting, apart from the fact that it collects certain numbers that mathematicians might care about. Again, on the calculational level, I already emphasized that this Riemann-Roch type integral is helpful in order to perform calculations. And these calculations are also doable by a trick that mathematicians have invented. It's the so-called splitting principle. And it says that all the quantities that I had under the integral can be expressed in terms of so-called Chern roots. They arise from the total Chern class, if you've ever heard about that, from a formula like this. But essentially, you have d quantities attached to your manifold M, called x1 up to xd, and from these you can calculate the entire expression that I had on the previous transparency. So you might remember the Hirzebruch chi-y genus with the so-called top class of M and the Chern character of this virtual bundle, which you may recognize from the first transparency. And then to do the calculation, actually you need these expressions, which are viewed as a formal power series in xj. So you should expand this expression here with respect to xj. And these are actually differential forms, so the integration makes sense at the end. So this is the classical part here, and then all the other infinitely many factors can also be piece by piece traced back to the ingredients that I had in this terribly complicated bundle, virtual bundle on the previous transparency. So believe it or not, but this expression here makes things tractable, and we can do calculations with them. Because if you take a closer look at these infinite products that I've written here, they may look familiar to you if you've ever worked with Jacobi theta functions. So everything can be repackaged into a convenient expression like this, where this is the first Jacobi theta function. Now, by construction, this is already a formal power series in Q and y to the -1 up to this prefactor that I just smuggled in for no good reason so far. But as soon as you see the theta functions occurring, you may become optimistic in terms of expecting modular properties for this function. And indeed, if the first Chern class of M vanishes, and that amounts to the sum of these xj to vanish, then this expression has wonderful properties. It's actually modular with respect to the entire modular group SL2Z. It's what we call a weak Jacobi form of weight 0 and index b12. And these things are very, very well behaved. So that makes calculations with these complex elliptic genera, again, calculable. So that was a really, really lightning review of the mathematical side of the story. There is a...
Sorry, Katrin, just to check, yes. Is the modular invariance looks like it doesn't depend on the integral over M. Is that correct?
Indeed, you can actually integrate here. At the end of the day, if we look at examples like K3 surfaces, and actually the examples that I will show you later on concretely for the ADE type singularities, the integral, you integrate out.
Yeah, but
so
the integrand,
tau and z.
The integrand itself is modular invariant.
Well, not quite invariant. So there's a certain factor that you obtain here. It's not quite invariant, it's covariant. But when the first Chern class vanishes, you get good modular properties here. So there's a bit of calculation you have to do because of the xj. So there's a coordinate transformation that you have to make. It's not completely immediate, but it's, well, as I tried to say, when you see this expression, you can get optimistic and then you check the calculation. And it actually does work as soon as the first Chern class vanishes, as soon as the sum of the xj vanishes. And that's something you see from the transformation properties of this expression here. Yeah. But yes, you're right. With this expression, you know how to deal with modular transformations. Just that you would want to transform tau and z, and xj is still kind of hanging out there. So you have to do something with xj and then perform some substitution or something like that. Yeah, indeed. But at the end of the day, the integral will have gone, but you will see in the calculation that I'll show you later for the A-type singularities, actually, I will remind you of this little discussion that we're having now. It's actually crucial that things come from expressions like this and that we're not scared of the xj. They're just differential forms. So the stuff really immediately attached to the manifold over here. Okay, very good. And if that was too quick, I hope I can just let you rest assured that, okay, I've just told you that these expressions here are well defined, and then in some cases we know how to do calculations with them. And the cool thing is that they have a physics counterpart in conformal field theory, where when I say conformal field theory, actually here we're talking about super conformal field theories, and I'm always speaking of unitary Euclidean theories, two-dimensional theories. And in my definition of conformal field theories, also the partition function is always well defined. So that's something I should say for starters. And then of course, concerning the supersymmetry, I want to focus on theories that have n equal to world sheet supersymmetry on the left and on the right, and space-time supersymmetry in addition. And the central charge better be an integral multiple of 3. Then, of course, these theories come with beautiful mathematical structure, but we can focus on just a few essentials here. Of course, there's a space of states. We can restrict our attention to the Nevers-Schwarz sector. And on the space of states, we have all these superconformal algebras acting, and there are 4 operators that play centered stage here. That's J0, L0, and their right-handed, right-moving partners. So these are the zero modes of the U1 currents, and L0 is the Virasoro zero mode, and I'm twisting it. I'm performing a topological twist. So I'm actually working with this operator L0 on top in the following. That's necessary in order to get to the elliptic genus later on. So these 4, mathematically, these 4 are just pairwise commuting operators that have simultaneous eigenspaces. So this space here decomposes into simultaneous eigenspaces of these guys. So they're mathematically reasonably easy to deal with. And all the simultaneous eigenspaces in full-fledged superconformal field theory are actually finite dimensional, which is important for later on. And in addition, we have, for instance, the left-handed extended n equal 2 superconformal algebra acting. It's extended due to the space-time supersymmetry. It's extended from n equal 2 in every case. So we could work with the setting all the way through, but we also may simplify things a little bit, because instead of taking the full Nevers-Schwarz sector, it's completely sufficient to focus on a subspace of that space, which is still infinite dimensional, but much easier to handle. Mathematically, it's just the kernel of that operator here. And in physics, it's just what is called the topologically half-twisted model. And the states in this space here are called quarter or half BPS states, depending on what all the other operators do to them. So that's still a fairly complicated space, but it contains all the information we need in order to deal with the complex, with the elliptic genera. Now, you could also push it a little further by not just taking a topological half twist, but by fully twisting. And that means that instead of just taking the kernel of the right moving L0 top, you should also take the kernel of the left moving L0 top. That's an even simpler space, and with all the assumptions that I listed for you, this always becomes a finite dimensional space. So clearly that's easier to handle.
Can you say what the twisting here is? Is it changing some of the bosons into variants?
No, not quite. The twisting is this thing here. The fact that instead of considering the usual Virasoro L0 mode, I'm going to consider a twisted Virasoro algebra, and the twisting amounts on the level of the operators that we need here. The twisting amounts to saying, okay, here's the new Virasoro, and that has actually central charge 0 now. Whereas over here, I had the central charge that I was talking about up there. Okay, so that's really, it's an important point, because we're changing our focus from the Virasoro 0 mode L0 to that twisted Virasoro 0 mode. So that's important here. All right. So if we're interested in these spaces and in the action of the remaining three operators here, we might be interested in the dimensions of common eigenspaces. And the usual way to, well, list such dimensions is in terms of these formal power series. So this here looks awfully like a partition function, not quite because of the signs, but the signs are very relevant here. So definitely this is a quantity that we might be interested in considering. And I've put the 0 tilde here in a bracket because it really doesn't matter for the result of taking this trace. It really doesn't matter whether you're taking the trace over the full Nevers-Schwarz sector or just over the topologically half-twisted space. And that is an effect of the worldsheet supersymmetry, which has the effect that you have lots of cancellations here in accounting for the coefficients in front of powers of Q and Q bar. So let's focus on Q bar. So what I'm doing here, focus on Q bar, and imagine that we have one eigenvector which contributes here, one common eigenvector. This eigenvalue with respect to L0 tilde top is non-zero. Then, due to the supersymmetry, that eigenvector will come with a superpartner that has the same quantum numbers over here, but contributes with the opposite sign over here. So the contribution from these.
Can I ask a question? What does the symbol A mean, to clarify, script A?
So A is the extended n equal 2 superconformal algebra. So we're taking the worldsheet superconformal algebra here, and then there's an extension to it because of the space-time supersymmetry. Okay. For instance, at d equal to 2, space-time supersymmetry extends your n equal 2 algebra just to the n equal 4 superconformal algebra. Okay. That's in some sense the simplest case, but also for the other central charges listed here, there is a certain extension that's going on. Okay?
Yeah, that's fine.
All right, so I was trying to explain the cancellations that are going on here. So any eigenvector contributing with a non-zero eigenvalue of L0 tilde top here will have a contribution which cancels out to the calculation of the trace because of contributions from the superpartners. So actually the expression that I wrote here is not dependent on Q bar, and if you choose to take the full Neveu-Schwarz sector here, the only contributions that we will count at the end of the day, the net contributions, will come from the kernel of L0 tilde top. So you might just as well take the trace over that topologically half-twisted model from the start. But of course, the same argument holds for the left-handed side. So also with this expression with just the 0 tilde here, still you have cancellations going on this side. And the only non-zero contributions at the end of the day come from the kernel of L0 top. And now you can remember, I told you this is a finite dimensional space. So what happens here is that just you sum up a finite number of pluses and minuses. So there you are with the integer. And there you are with a nice...
Can it vanish over the trace?
It can vanish. Yes, definitely it can vanish. Yes. For instance, if you're looking at a superconformal field theory associated to a complex torus, then this will always vanish.
Okay, right.
But this is the invariant we've been looking at. It's known in physics under the name of the Witten genus. It's an invariant in the sense that when you consider a family of superconformal field theories, the left-hand side, a family with depending continuously on its moduli, then the left-hand side will depend continuously on the moduli. The right-hand side is an integer. So there you have an invariant. It's known as the Witten index, and I denote it as chi of h for good reason, because in those cases where you're working with nonlinear sigma models, this invariant is expected to agree with the Euler characteristic of the underlying manifold. So your question translates into the question to me whether there are manifolds with vanishing Euler characteristic, and I gave an example of one manifold.
Okay, so that's why the torus comes in.
And does J naught minus J naught tilde have the meaning of a fermion number?
Indeed.
Okay.
Indeed, yes. That's almost hidden in my assumption here that we are working with space-time supersymmetry. It says that these two are linked in that way. Indeed. And actually, this equation follows from an even stronger expectation, namely that this topologically fully twisted space, which I told you about over here, actually can be identified with the cohomology of the manifold, the underlying manifold. And there's bigrading here through holomorphic and anti-holomorphic form degree, and that translates into the bigrading that you get over here to the eigenvalues of J0 and J0 tilde. So that refers to your question as well. And if that is true, then this equation actually follows immediately. And if this is true, also, we see that we cannot only determine the Euler characteristic of the manifold through these quantum field theory data, but we can also refine and get the Hilfsbruch Chi genus, taking the trace still over this finite dimensional space, and now replacing this operator here by the one where I've replaced the -1 to the minus J0 to minus J0 by minus y to the J0, just as we did in the geometric setting. So from this, again, that will follow. And now, of course, we would like to refine further to obtain an analog of the complex elliptic genus that I told you about. And that's also possible with a simple trick. Now we're replacing this space here in our definition of the Chi genus, in our conformal field theoretic definition of the Chi genus, replacing this finite dimensional space by the topologically half-twisted space. And other than that, I've just copied that operator. And this is what we call...
Sorry, by Calabi-Yau in this case, you don't, it doesn't necessarily need to be a threefold. Okay, so it's a general...
It does not have to be a threefold. It's general. Yes, indeed.
Yeah. And the Calabi-Yau property that you're using is that it is...
C1 equals 0.
C1 equals 0.
C1 equals 0, indeed. Yeah. I want C1 equal to 0 because in other cases, you might still have an identification like this, but I cannot say much about it because I don't know cases where that's been proved. But the expectation that this geometric approach that I gave first and the quantum field theory approach that I'm giving here, that they actually lead to the same expression that can be checked at least for complex tora and for K3 surfaces. And also for Calabi-Yau manifolds at higher degree if you allow yourself to perform orbifold constructions. So at higher, not degree, at higher dimension. If you allow yourself to do orbifold constructions, then knowing that everything works out when you start with the complex torus actually shows that this holds in quite good generality.
And C1 equals 0,
Yeah.
just to double check if I'm remembering correctly, C1 equals 0 means that the holonomy is SU rather than U. Well.
Exactly.
Okay, all right.
Exactly, yes. And for me here, just on the level of these expressions here, it means that I get this modularity property, which just makes life much easier, because then you're finally working in a space of functions, which is very, very well under control and actually finite dimensional, if you want. Okay, so here we have a definition of the conformal field theoretical elliptic genus. And as before, you have these cancellations going on. So the fact that I put the Q bar to the L0 tilde top in here is just show, because it doesn't enter. At the end of the day, you have cancellations from any contribution that comes from non-zero, from eigenvectors with non-zero eigenvalue with respect to this operator. So indeed, we have a power series in Q and Y to the -1 up to this prefactor, which I smuggled in order to get this modular property that I like so much. And also, it won't be relevant for what follows, but it doesn't matter. I would prefer to define this for this talk. I would prefer to define the conformal field theoretical elliptic genus just on the topologically half-twisted model, but it doesn't matter because of the cancellations that I mentioned previously. You can also take the full Schwartz sector. The result of taking this trace is just the same expression, no matter what. So I already said that the expectation that all these invariants agree can be checked in certain cases. In particular, for K3 surfaces, we can check this. Although you have to take the statement with a grain of salt. So when I talk to mathematicians, I do admit that this has to do with the fact that we have to get our definitions right. So we actually come up with an appropriate definition of what a conformal field theory associated with K3 should be, and then the expectation actually holds true. And knowing this fact here, this expectation is incredibly useful in order to come up with such a definition. Now, just as a word of warning, although it's not the topic of this talk, over here we had this very nice identification of a subspace of the space of states in our quantum field theory on the one hand, with these geometric data, the cohomology on the other hand. And given that I'm telling you that this is an equality that we should expect to hold, it's very tempting to identify the topologically half-twisted model with the cohomology, which underlies our geometric definition of the complex elliptic genus. That was built on this virtual bundle that I introduced. So to expect this space here to agree with that space is something very, very natural. And that is done all over the place in the literature, but it's actually wrong. It is not true that these two spaces agree. This one, in some sense, is much bigger. Both have the same graded Euler characteristics, so that this equation here can hold true, at least in the cases where we can check it, but the spaces don't agree. It's not that dramatic because we do have geometric constructions of the topologically half-twisted model, so one can fix this, but just as a word of warning, even though here we're still walking on ground that has been classically checked, there are still some open and non-trivial observations that you can make there. But I wanted actually to tell you about some new calculations that I've done with my PhD student, Yuhang, and there we want to address singularities. So now I should turn to discussing these singularities. So the relevant singularities here occur in orbifoldings. And again, I'm going to start with the geometric side of the story. I'm going to start with the Calabi-Yau D-fold and with a group action on it by a finite subgroup of SU2. So that's where your holonomy group comes up. And it should act holomorphically, and it should leave the holomorphic volume form invariant. I'm making these assumptions to make sure that the quotient, even though it will have singularities, is still reasonably under control. These assumptions ensure that the quotient can be resolved. You can resolve the singularities, and the result will again be a Calabi-Yau D-fold. I call it the gamma orbifold of M. There is a conformal field theoretic counterpart to these orbifold constructions, and actually, historically, it precedes the geometric orbifoldings. And of course, one always hopes that things are compatible in the sense that it doesn't matter what I do first, whether I first associate a conformal field theory to the manifold and then do the orbifolding, or whether I go the other way around. And indeed, at least for the case d equal to 2, we can prove this. And that goes back to work that I did together with Werner, who's here today. And that was done in my PhD thesis. And we can show that indeed, in the case d equal 2, where there are only two types of complex of Calabi-Yau defaults, namely the 2 torus and the K3 surface, with all the notations that I introduced above, it is true that the superconformal field theory associated to the geometric gamma orbifold agrees with the conformal field theoretic gamma orbifold of a theory associated to the non-orbifolded manifold. And again, one should say this has to do with the fact that we got our definitions right, but this is really reassuring, and that you do need to prove quite a bit here, even from the definition that we started out from. Okay, so that's the context in which this PhD project of Yuhang's actually takes place. For K3 theories, now the elliptic genus is very well under control. And I remind you, the original question I asked was, shouldn't it be possible, since we understand that elliptic genus so well, shouldn't it be possible to decompose the elliptic genus into contributions that come from the non-singular part of the orbifold on the one hand, and into contributions from the singularities on the other hand? So let's briefly see what kind of singularities occur in this K3 context here. From the orbifoldings, the singularities that can occur are called simple surface singularities or ADE type singularities. And these are well under control and have been classified. And here's a quick review of that classification and of what I mean by having these singularities under control. So first of all, these singularities can be classified quite easily simply because the finite subgroups of SU2 have been classified. There are 2 infinite series and 3 exceptional cases, and it's not so difficult to picture these groups explicitly if instead of working in SU2, you work in SO3. So describing the groups in terms of subgroups of SO3, and then you still need to lift them to subgroups of SU2, and that's what this word binary actually signifies. But the finite subgroups of SO3 are known. So for instance, you can have cyclic groups. These are just rotations about a fixed axis, cyclic groups of some finite order. Then you make it a little more complicated by adding a rotation by 180 degrees about an axis which is orthogonal to the axis that you used here. Those are the dihedral groups. And then you have the rotational symmetry groups of the Platonic solids. So these are the cases that can occur. The singularity in the origin of this quotient here then is well under control in the sense that we know exactly how to resolve it. The resolution here comes from blowing up several times, and every time one blows up, one replaces the singularity that still remains by a CP1 or maybe a collection of CP1. Sometimes blow-ups can produce more than one CP1 in one go. And it's so at the end of the day, what happens is that in this quotient here, you replace the singular point by a collection of CP1s, or topologically, these are just 2 spheres. So by a collection of 2 spheres, which I symbolize by these blobs here. And the form of this so-called exceptional divisor, that's the thing that you glue in instead of the origin to make the surface non-singular. The structure of the so-called exceptional divisor is very well known and can be depicted by these Coxeter-Dinkin diagrams, which many of you probably know from the context of Lie algebras and Lie groups. So the same diagrams, the ADE type diagrams, and you can read them as follows. Each of the nodes here corresponds to one of the CP1s in the exceptional divisor. It's also true that any 2 of these CP1s intersect transversally. So either the intersection is empty or the intersection is just given by a single point, and then the tangent spaces actually add up to the tangents, generate the tangent space of the full surface. And whenever that intersection is non-empty, then I will connect the corresponding nodes in the diagram by an edge. So that's how you can read these diagrams as telling you exactly what the structure of the resolution here looks like. And the left-hand column is not so important for what I'm going to tell you about. In the calculations, we need the left-hand column. This is just a description of these singular surfaces in terms of an algebraic variety given by the zero set of some polynomial in C3. So you can see that you have surfaces, and you can immediately check that all these surfaces have singularities in zero, and these are the descriptions of those quotient singularities. And Arnold introduced the classification of singularities where these ones are precisely the so-called simple singularities. So those singularities are at the center of attention from now on, and I want to calculate elliptic genera for them. To ease notation a little bit, I will use the letter AK, DK, or EK, both to signify the finite subgroup of SU2 that is needed and the resolved singularity. So the thing where we glued in the graph that I showed you previously. Now, how to calculate an elliptic genus? Turns out that the quantum field theory approach is much easier here. And I also told you that in order to calculate an elliptic genus, you don't need the full-fledged superconformal field theory. It's sufficient to consider a topologically half-twisted model. So we should try and construct a topologically half-twisted model associated to this geometry, and then determine its conformal field theoretic elliptic genus according to the formula that I gave you earlier. And to start out with the easiest case, let's work with the trivial group gamma for starters. So let's work on C2. Should be a free field theory, shouldn't be too problematic. And indeed, you can even construct the full-fledged superconformal field theory here. It doesn't have a well-defined partition function in the sense that I said earlier, but still you can, of course, construct a free field theory just on C2. And for the topologically half-twisted model, then this is the space of states that you get. Many of you will be familiar with this. This is the Fock space representation for just two free bosons and two free fermions, which are the superpartners of the free bosons. But everything formulated in terms of this topologically half-twisted language. So we have two sets of bosons here, denoted by where the modes are denoted by A and K and B and K. K runs from 1 to 2, so those are the dimensions of C2 that you need to use. And the moding here, I'm using the modes so that in the Fock space you have only the positive modes for A and K and the non-negative modes for B and K. So that's what comes out from constructing the Fock space representation here. So these are the bosonic degrees of freedom, if you want, and all these commute because I'm restricting to these positive or non-negative modes. So all these commute, that's why I'm writing it in terms of a polynomial space here in infinitely many variables. And back here you have the fermionic partners. The phi's are the partners of the b's, and the psi's are the partners of the a's. And then it's easy to construct a free field realization of the n equal to super conformal algebras that act here. We only need these three special operators. L0 top is made to measure the energy. So this is just the label that I have for in the index for each of these modes. J0 is the U1 charge. So the bosons are uncharged, the fermions are oppositely charged, and there's nothing going on the right-hand side here. So everything has charge 0. And then I'd like to calculate this quantity because that's exactly the expression that I gave you for the conformal field theoretic elliptic genus earlier. I've inserted the central charge 6 here, which is the central charge that you have for the underlying conformal field theory. And then you immediately notice this is terribly ill-defined because all the coefficients are infinite. And the troublemaker sits right here. We have the 0 modes of the bosons BK0, which have quantum numbers 0 all the way through. And this means that whenever you have an eigenspace, which is any given quantum numbers for J0, J0 tilde, and L0 top, it will come with infinitely many friends obtained from just taking polynomials in B0K and acting on it. All of those will give linearly independent extra contributions. So every single coefficient in here is infinite. So this expression doesn't make sense. But as an established method to deal with this, if one can find an appropriate symmetry on this model, then one can actually define a equivariant version of this. And here the symmetry is easy to find. We just take C star equivariant notions. You just take the C star action on C2, which multiplies everybody by a complex non-zero number. The BK actually correspond to the coordinates of C2 in our geometric interpretation. So it's not hard to argue that the BK should be multiplied by Xi. The phi KM are the super partners of those, so they are treated just the same. And then to be compatible with the underlying Lie algebra structure, which I'm hiding over here, actually these must be multiplied with Xi minus 1 and Xi minus 1 respectively. And then the equivariant version of that expression actually is well defined. This gives a nice quantity, which we calculate as follows. This is what we're supposed to calculate. And again, this expression might look familiar to you. You can trace back every single factor to part of the Fock space that I gave you earlier. So for instance, here you see the contributions from the BMK. There, K is 1 or 2, so that explains the exponent here. M is n minus 1, because m starts from 0 and n starts from 1, so that's okay. So here we're treating the bosonic modes BMK. Here we're treating the bosonic modes A and K, and the fermionic modes are taken care of up here with exactly the action of Xi that I had on the previous transparency. And again, we happily observe that this can be rearranged into an expression in terms of Jacobi theta function. So that's nice and elegant. That's the result of making things equivariant here. And of course, as expected, this has a pole at zeta equal to 0, for instance. And that should be the case because we already found out that the non-equivariant elliptic genus is ill-defined. So that's just the pole that we observed previously when I told you that the B0K are the troublemakers. We also observe, again, a modularity in this expression here if we act appropriately on all the parameters. And this means that from here, we can actually apply our standard orbifolding methods to calculate the elliptic genera on the conformal or the quantum field theory side for all the ADE type singularities. For instance, for AK, that was the orbifolding by a cyclic group of order K. You get an expression like this. For any of you who has ever calculated with conformal field theoretic orbifolds, you will be not surprised to see an expression like this. We're dividing by the group order here. That's what you expect. And the summation, on the one hand, the M summation makes things invariant under the ZK plus 1 action, and the N summation runs over the twisted sector. So these expressions, of course, the details have to be checked, and we did that, but these expressions, I think, are very expected. So here we have a closed formula for an equivariant version of an elliptic genus for AK type singularities. And this formula already occurs in a paper by Harvey, Lee, and Murty, who arrive at the formula from a different perspective. It's also not their main interest here. So their calculation is much more complicated, but they want to do different things with it. They perform a gauge linear sigma model construction in order to arrive at this equation. And for us, it's just reassuring to see that somebody else had this formula as well, up to a difference in a sign, which mathematically is not terribly relevant. And I hope this is convincing enough for the other groups to proceed the same way. It gets a little more complicated because the other groups have slightly more complicated structure. The ingredients will always look like these ingredients. You have summations where maybe then there are extra prefactors here. So things get a little more complicated when you write out the formula. But the basic ingredients always look like this, so it's not very surprising that you can rearrange everything so that also for DK, E6, E7, and E8, everything can be expressed in terms of the formula that I gave you already here. So this is just—
Sorry,
yeah?
Katrin, just a query. In the Harvey, Lee, and Murty calculation, were they using the same sigma model? You said it was a gauge
yes,
sigma
they're using
model.
the same sigma model. They're working on C2.
And what is zeta somehow related to holonomy of that gauging?
No,
Or it's some U1 factors around
yeah, so
cycles.
actually I will come to that later. Of course, it's more natural here from that perspective just to work with U1, but you see immediately that you can extend to all of C star, and that'll be quite relevant in a little bit when we go back to U1 in an immediate step. Yes, indeed. So this is actually U1 action at the start. Yes. Okay, so, but these formulas were not given in their paper, I assume, because it's harder to do the calculation with that approach. And also, as I said, they weren't primarily interested in producing formulas like this. So here we at least have a closed formula for everything. But what about the geometric counterpart now? A priori, we can be optimistic because this idea of introducing equivariant versions of indices is, of course, also widespread in mathematics. There's ample literature on equivariant index theories. It all goes back to Atiyah Bott and Atiyah Singer at the end of the day. And here's the version that we would like to use. If M is a compact d-dimensional manifold and C is a compact topological group acting holomorphically, then we can introduce an equivariant index where the equivariance is given by a twisting by any group element here. And the recipe to do the calculation is as follows. You need the fixed point locus, you decompose it into its connected components. Then the tangent bundle restricted to any of these components will decompose into a direct sum of eigenbundles. G has an induced action on that tangent bundle, and the eigenbundles are labeled by the respective eigenvalues. Lambda, which I write as e to the 2 pi I zeta L. Then again, we need those Chern roots with the trick of the splitting principle. And then the equivariant elliptic genus looks very similar to the genus that we saw before, with the Sulzberg-Riemann-Roch type integral, where, however, you only integrate over the fixed point locus. And in here, you have some expressions that do depend on the action of G, because you see the eigenvalues, lambda equal to 2 by I zeta L, occurring in here. So again, this looks a little bit complicated on first sight, but one can actually do calculations with it, and we'll see an example in just a minute. So here's a nice formula, but we're in trouble because it doesn't apply to the setting that I was talking about. I want to apply it to the ADE type singularities, where the space is non-compact, and I wanted a non-compact group, namely C star. And at this point, it really paid off that the student that was working on this had a physics background. So he essentially started to do the calculation without caring about the fact that not all the assumptions hold, because he observed immediately that we can do the calculation as long as we choose G to make this space compact, because then the integral here will be well defined. And then once you've seen that you get sensible results, then you can check with the index theorem that even in the non-compact space, actually the cancellations that lead to this localization here, the cancellations still go on if you're working on a non-compact manifold. So if we want to apply this formula, we need to choose G accordingly as to make the fixed point locus compact. So the identity is not allowed, but in general, all the other values of G that we like will be, most of the other values will be allowed. And concerning the group, Denjo already lifted that mystery. Instead of working with C star, we will work with U1, and that's what Yuhang originally also did. And then only after the fact, one notices that there's nothing wrong with extending the values of zeta here from real numbers to arbitrary complex numbers. So to be safe, you should start working with U1 here and then extend later on. All that said, one can start doing the calculation, for instance, for A1. Remember, that's a Z2 quotient of C2. So to resolve that singularity in 0 here, one only needs to blow up once, and the exceptional divisor has just one component, that is CP, that is 1 CP1. The C star action was given by just multiplying with complex numbers. So for the original C2, the only fixed point is 0, or singular point. But when you multiply a line through 0 by a complex line through 0 by such a number, it is mapped to itself. So if you remember how blow-ups work, then you will notice that that means that actually the exceptional divisor is completely fixed under the C star action. So our fixed point locus is just the exceptional divisor, assuming that psi doesn't act trivially, so I have to exclude +1 and -1. In the formula on the previous page, I needed the holomorphic tangent bundle restricted to the fixed point locus that decomposes. It's a two-dimensional manifold, so this should decompose into two line bundles, one corresponding to the eigenvalue 1, that's just the tangent space of CP1, because CP1 is fixed under Xi, and the other eigenvalue one has to calculate, and this is actually where one needs Arnold's description of the singularities in order to get to this eigenvalue here. And now I insert into the formula that I gave you. We integrate over CP1. We copy out these churn roots, there are two of them here, and then this product here takes into account the two eigenvalues that we've read off. So here we have zeta equal to 0, or zeta lambda equal to 0, and here we have zeta lambda equal to 2 zeta, which is what we get from here. Okay, now that looks a little bit terrible until you remember that x1 and x2 are churn roots. So these are actually represented by differential forms of degree 2 here. We're integrating over a real two-dimensional manifold. And if I ignore all the theta stuff back here, actually the expression that's written here in blue would just give the usual Euler characteristic of CP1. But we do have the thetas. But now you see how you can do the calculation. You just expand this expression as a formal power series in x1 and x2. And all you need is the leading order term, because to integrate over something that of real dimension 2, you only need to pick up the differential forms of degree 2. And it also helps to know that the first Chern class here vanishes. So minus x2 is plus x1, and the calculation just boils down to applying a L'Hopital rule to this expression, and you can actually almost see that we've done that explicitly down here. So that's a closed formula for the geometric version of the equivariant elliptic genus on an A1 singularity. And you can apply the very same technique for all the other singularities. We have closed formulas for all the other singularities from this perspective. So that's cool on first sight and disappointing on second sight, because the formula is actually quite complicated and gets more complicated for the more complicated singularities. And quantum field theory gave such an easy expression, actually. Just a nice sum that I wrote down. But there's a happy ending with a good deal of theta function gymnastics. You can actually show that both results agree. So we have two approaches now to come up with a version of a C-star equivariant elliptic genus, and both approaches give the same result, and that's very reassuring. It's another case where geometry and conformal field theory really work together well, and where orbifolding actually is implemented in a natural way. So we now really have a good way of arguing why this should be the right definition of an elliptic genus for an ADE type singularity. So, and of course we have to exclude those values where Xi acts trivially. Here I'm a little bit overly careful. If you exclude all the roots of unities, all the roots of unity by orders that divide the order of the group gamma, then you're safe. Both sides are well defined. But this is actually a nagging point now, because the start of this project was my question whether I can understand the K3 elliptic genus by decomposing it into stuff that comes from the singularities and stuff that comes from the non-singular part. I cannot introduce a C-star equivariant version of a K3 elliptic genus because C-star doesn't act there. So I'm stuck because I can't use this. On the other hand, I can't just set zeta equal to 0 here. I'll get infinity. It's ill-defined. So we do have to regularize in order to make sense of things, but that also can be done. And again, we're taking inspiration from the string theory literature. For instance, the early paper by Dixon, Harvey, Waffa, and Witten, where they come up with the idea of defining orbifold Euler characteristics. And remember, we're using the Euler characteristic and refining it to get to the elliptic genus. So this is a good starting point. So what they do is they have a Cavalier default and again a group gamma acting as before. Now I'm assuming that the singularities actually come as a discrete set of points for the formula here to make sense. And then one can argue that for each of the singular points, one can define a orbifold Euler characteristic that's now a rational number, not necessarily an integer anymore, but it's cooked up so that the Euler characteristic of the orbifold decomposes into this part, which comes from the original manifold, from the Euler characteristic of the original manifold, and a separate contribution from each singularity. And using this idea, we just translate into the language of twisted or equivariant elliptic genera. We're using the quantum field theory description, and we're putting our finger on the contribution to our formula, which has the singularity at z equal to 0. And this is the troublemaker. The original half-twisted model on C2, we observed it doesn't make sense at zeta equal to 0. We very explicitly observed how it doesn't make sense, but this is actually the only divergent term in our C-star equivariant elliptic genus. So we get rid of it, and this is exactly the analog to the construction that we see up here in the literature. In fact, this is a regularized version of the C-star equivariant elliptic genus in the sense that we can now send zeta equal to 0, and the right-hand side remains well defined. And when we insert z equal to 0, we, for the elliptic genus, we always recover the Euler characteristic, and that also happens here. When we insert z equal to 0, we actually recover the regularized orbifold or Euler characteristic that is known from the literature. So this looks promising, and all end as well. Actually, when we apply this to the full-fledged Calabi-Yau two-folds with all the restrictions on the group actions that are listed before, let S denote the set of singular points in the quotient, and let gamma S denote the type of singularity in the point S. Then with this definition, we have an equation where the elliptic genus of the orbifold is decomposed into a contribution that comes from the elliptic genus of the underlying manifold on the one hand, and a separate contribution from each of the singular points on the other hand. So we were very pleased with that result. And in the last 3 minutes, if I may, although I'm noticing I'm already a little bit over time, I would like to.
There's no need to rush, Katrin. We're not pressing anyone for time.
Okay, perfect. Because, okay, so this is actually the final note to the original question that I asked. But Yuhang had also observed these relations between the elliptic genera, the C-star equivariant elliptic genera of the different singularities. And I put that under the rug a little bit when I gave you the formula. I said, well, this is just a technical way of writing things more conveniently, so I don't have to fill the whole transparency with theta function expressions. But it is kind of odd that the dk+1 singularity can be expressed in terms of A-type singularities. Shouldn't there be a geometric reason for that? And here is the reason for that. We learn how to do this from beautiful work by Slodovi, who among many other things teaches us the following. If you want to consider the resolution of an ADE-type singularity, you can do that in several steps. Each of the relevant groups gamma here has a Z2 subgroup, but you can just divide by that first, do the resolution, and then act with the residual group on the resolved space. This is always well defined, and the result will again have, in general, several singularities, resolve them, and then you get the original resolved ADE-type singularity. Now, the red guy here that I started from, we just had a look at that previously. That's the A1 type singularity. The resolution is just given by an exceptional divisor, which is just a single CP1. And on the left-hand side here, I'm depicting that as that red dot. The residual group gamma in the dk+2 case, the dk+1 case, actually will have 3 singular points on that CP1, and they all produce A-type singularities. So now it's not surprising that these legs grow out. But one has to be a little bit careful in the description. Actually, the way you calculate this is, again, by lifting, by doing a Z2 lift here. So the singularity arising over here that produces this one node as a leg over here is not an A1 singularity, although you might expect that on first sight. What it actually is an A3 singularity, which is folded by Z2, and the middle node then is glued heads on to that red node. So this guy here comes from an A3 singularity folded into half. So that's actually half an A3, That's half an A3, and that's half an A2k minus 3. So now you see why this formula has to be correct. We have the half A2k minus 3, and we have the half A3 twice. But now we've overcounted a little bit, because from each of these legs, we got a contribution of 1/2 A1 accounting for the red node. That gives 3/2 A1 altogether. That's clearly 1/2 too many. So we make up for that by subtracting it at the end. So that looks a little vague, but as I said, one can put it onto solid ground by using Sloterdijk's result. And mind you, we actually first had the formula and then looked for a geometric interpretation. So the formula is correct for sure. And it works for the other cases just as well. So here for A6, in the middle node, you will see a half A3 entering, and you will see 2 half A5s entering on the right and on the left. So that's what you see here. Again, overcounting a little bit, you have to make up for that. E7, you have a half A3, a half A5, and a half A7, correct for overcounting. And E8 now is almost boring. The only difference between E7 and E8 is that the A7 gets replaced by an A9 here. So that's that, and that's the geometric interpretation of these relations between the elliptic genera for the ADE type singularities. So now we feel fairly confident that we have the right definition. And I should have added on the previous transparency that there are actually already other notions of regularized elliptic genera in the literature. In particular, there's one by Iguchi and Taormina, and another one by Cheng and Harrison. And there's a piece of homework that we haven't quite completed yet, and I would like to complete that before putting the paper on the web. We are certain already, because we have the formulas, that both these definitions are different from ours. They just give different formulas. But we don't know very well yet how the different approaches actually relate to one another. So that's certainly something I would like to know better before I say we have a good definition. And that's that. And I thank you for your attention. Apologies for running over time a little bit, even though there's no rush at this.
Okay. Thank you very much, Katrin. And the floor is open to questions.
Can I ask another question? Because I have to leave in a minute. Have you got any thing to say about higher dimension singularities? Or is it just over?
Not yet, but of course that's the next natural step, and everything we've done here would work in higher dimensions, just that the singularities get more complicated. And also one has to think about what to do with non-isolated singularities there. So in higher dimensions, what often happens is that you have curves of singularities. Of course, one can treat them as well, so one would have to integrate here instead of summing. So in principle, I think one can play similar games in higher dimensions. There's no reason to expect K3 to be special here, but I don't have any concrete results to say here.
I mean, a singularity, you know, of positive dimension. I don't mean working just in higher dimensions. So, I mean, what is the most sensible, easy, natural example to work on that you could understand this phenomenon? Is there one? Do you understand what I mean?
No, sorry, I didn't get your question. I didn't understand your question.
So you said that in principle these things would work. So what is the natural example that you would look at first? Is it convoluted?
Complex 3 torus divided by a product of two Z2s, for instance. That's a natural example to look at.
So what are the
using
singularities?
Calabi-Yau threefolds through orbifold methods from tori again.
So what are the nature of the singularities there? Do you know offhand?
I don't know offhand, actually. But it's, again, quotient singularities, so there are standard techniques to deal with them.
Yeah.
And the Equivariant Index theorem, which we used here, I mean, at no place I really made terrible use of the fact that we are in 2 dimensions, just that the calculation is tractable because well, we only have to deal with one Chern root here. But in principle, I don't see any problem with applying this technique in higher dimensions.
Yeah. And what about quotienting by a continuous action?
Oh, I don't know how to do that, actually.
I mean, that's what would be a natural thing to.
Yes, that would be natural, but then I think this.
Well, the equivariant machines exist, so I mean.
Yeah, that's true. That's true. Well, now the singularities are a different type. Of course, here the symmetry that I'm making it equivariant by that is continuous, but not the nature of the singularity in the quotient that you're performing. So I don't know, you could take the viewpoint to say that the torus is actually just it's not continuous, it's an infinite group that I'm dividing by, so not a good example. Yeah, I just don't know the answer to your question, I'm sorry.
Thanks very much, very nice talk. Actually, I have to go.
Do we have other questions? Okay, we'll see.
Yep, I have a number of questions. So the first thing is that here you get a very nice separation of contributions to various cohomology groups. Now, usually people talk about that in the language of motifs. So have you thought about how to put these things together?
That's an open project. Indeed, I think this is very important now to go down that route, to actually make things, to come up with categorical language here, or to even go a step further and introduce motifs, indeed. But there's nothing concrete I can say. Yes, definitely that's the direction that one needs to follow now. There's so many bits and pieces where we can see that things fit together, because symmetries fit nicely with between conformal field theory and geometry, and really one should put that down into a unified picture by using the language of motifs, definitely. Yeah. But I don't have any concrete thing to say.
One of the things in the old times which I did not really understand is how discrete torsion comes into the game. And presumably you say you know the right definition, so you have a way to handle that.
Yeah, that can be handled in this setting. So the discrete torsion on the conformal field theory side is just a choice of the symmetry action on the twisted sectors. So there it's actually mathematically easy to say what discrete torsion is, and also it's easy to see why there should be this degree of freedom. Well, not for these abelian groups here, but essentially you observe that you can put in extra phases here. You can actually motivate them. Not in this example, but in non-abelian examples. You can motivate extra phases here by looking at the twisted sectors separately. And on the level of the geometry, one can treat this by, one can treat this by treating the B field appropriately. So at the moment, I've just been speaking about classical geometry, and I haven't really introduced degrees of freedom for the B field on the geometric side. But of course, one can do that by introducing gerbs and gerb connections, and then discrete torsion also has a very natural explanation on that side. Yeah, I'm afraid we don't need motifs to include discrete torsion, but we do need motifs to understand better the nature of the topologically half-twisted model. Where is it?
Yes.
Here, I mean, I'm introducing this kind of by hand from the conformal field theory side. I emphasized that there is not an equality here, but one can construct a geometric version of the topologically half-twisted model by using the Cairo-Durham complex. That's the first time ever I've seen really some news coming from the Cairo-Durham complex, because the cohomology of the Cairo-Durham complex is different from this guy here. And that hadn't been observed for a very long time. We all thought they're just the same thing. And but the Cairo-Durham complex was made to give a mathematical treatment for the topologically half-twisted model. And at this point, when I try to implement orbifold techniques on the Cairo-Durham complex, I think I do need more categorical language to actually really understand how this space relates to the space of states abstractly on the level of conformal field theories or families of conformal field theories. So that's the point where I really think we will need to use this language, and it's definitely high up on my list of to-dos, because I think ultimately this is the only way to, for instance, treat all this Mathieu moonshine business and to find really good mathematical answers, rather than just putting together pieces of evidence for nice equations that we can find.
Do you have an idea how far you would have to go to that road? Would two categories be sufficient?
I hope so. As long as I'm just using conformal field series on the sphere like I'm doing here and hiding it just up to genus 1, I think two categories should.
Okay.
But anyway, the way it is that you start learning it and then you notice that you haven't learned enough and then the next step is easy as long as you weren't afraid of it before taking the first step. So I don't mind that much when the test is started at some point.
Actually, I probably think you could understand it much better than people who do it as a kind of abstract nonsense, because you know the right examples.
Yes, I hope so.
And since you mentioned the B field, I never could explain that in a really nice way. And can you know the value of the B field you get at the orbifold points?
Oh. Well, that's a complete different tool set that I would have to introduce. Maybe this way. Here, I'm saying that the topologically fully twisted model has the advantage that we're actually back to cohomology. That's a finite dimensional vector space. So for K3, of course, we don't have that many contributions here. We have H0, H2, and H4. That's the degrees that enter. When I explain things without introducing the B field on the geometric side, what I actually do is I'm restricting my attention to H2, and maybe I'm giving you a little bit of extra information, telling you what the volume is in a geometric interpretation or stuff like that. So I'm really only restricting to H2. And the whole magic of these descriptions here lies in the fact that I haven't given you a grading a priori. And the way the grading is chosen depends seriously on the B field. And you cannot make that compatible with the orbifold actions unless you kind of re-choose your grading after orbifolding. So that's the best I can do now free-handedly to say that the B field is actually somehow hidden in here when I'm saying I want to identify all the structure on the left and the right. Actually, there is a bi-grading here, and one has to be careful in writing out the maps because they do depend on choices that you make.
Yeah. Okay, thanks. Just one other remark. Yesterday in Arthur Jaffe's seminar series, I listened to a talk by Jens Hoppe, and also he was referring to work by Peter Slotowey, and I certainly am always happy when I hear that his nice work enters into things which are happening now. And of course, I liked your talk very much.
And people are not so aware of his work, but there's so much stuff hidden in there. I mean, this is a fairly natural thing to expect, but he really explains it in a nice big context. And even the mystery that the Dynkin diagrams are more familiar to us in physics from the Lie algebra perspective, that's not a coincidence here. Even that mystery is lifted in Slotowey's work. So you can understand the geometry here in terms of Lie theoretic data. And that's not just using labels and using pictures, but it's actually the Lie algebra structures entering in the deformation theory of these singularities. And that's also something beautiful, which I think Slotowey, it goes entirely back to Slotowey.
Yeah. Thanks.
Very good. Are there other questions? Well, if not, let's thank Katrin again, and we can go to less formal discussion. Thank you for a fascinating tour de force there, Katrin. I'm going to stop the recording. Okay.